you. You're gonna put in front of my face. It's gonna make me want to get in business with you. You're not doing it to get in business with me. You're doing it to keep me from getting into business with Tony
Muted. Miss Good, can you hear me now? Hello, hello.
Yes, I can hear you.
Okay, I'm sorry about that. I completely forgot about you. Like out of sight, out of mind kind of thing. I apologize. Okay. Let me briefly recap. I don't know if you have been following. Hold on, did I share my screen?
No.
I didn't share my screen. I'm screwing up today. I'm screwing up today. Okay, I'm just going to briefly go over what I talked about earlier. I'm sorry about that, which means that I have to apologize to the students here because I've been boring them to death now. So, okay, so basically what I was saying is that we're going to talk about chemical reactions in aqueous solution. So let me go back to my big screen thingy. Move this over here, move this here. Okay, so the first thing I talked about was the electrolytic, or I should say the electrical properties of aqueous solutions with respect to charges. And I briefly talked about the nature of charges, which is important for us to understand what we'll be getting into in this particular chapter. So this diagram here is a purely hypothetical situation where we have particles suspended to a fixed object up here. If both particles are neutral, then there will be no attractive or repulsive forces between these two because they have no charges, right? But here in this situation where you have the charges that are opposite to each other, if they're close enough to each other, then they'll be attracted to each other, right? So basically, unlike charges will be attracted to each other. In these two situations here, where we have two like charges, both positive and both negative, the force that will exist between them will be forces of repulsion, right? So basically, to summarize what this is describing here, is that if there are no charges, then there's no attraction between the particles. If the charges between the two particles are the same, then there'll be repulsive forces between them. If the charges are opposite to each other, there'll be attractive forces. And I was saying to the group that this is very similar to what you would observe when it comes to magnets, right? If you used to play with bar magnets, you see that if you bring two identical poles to each other, they will repel. But if you bring the north pole of the one magnet in close proximity to the south pole of the other magnet, then there'll be a repulsive force, right? So basically, there's a lot of similarities between how opposite charges behave and opposite poles of magnets behaves, all right? So now, I think this is where we got to. We started talking about aqueous solutions which contain ions. And what you'll find is that these solutions can conduct electricity, right? So this setup here is showing you where you have an external circuit, you have this electricity source, which is basically a series of cells. So collectively, we call that a battery. This is a positive end. This is a negative end. They are connected by wires to these two electrodes. These metal plates are called electrodes. They're usually metal. Sometimes it's made of graphite because graphite can conduct electricity as well. And what you'll find is that this one, which is connected to the positive end of the battery, is known as the anode because it's positively charged. And the cathode is the one that's connected to the other end of the battery, which is known as so this is known as the cathode. And what you'll find is that the negative ions will be attracted to the anode, the positive ions will be attracted to the electrode. So you're going to have a flow of current, not only in the external circuit, but also within the solution as well, right? So that's basically what is happening in this sort of setup. One thing I didn't mention before, so you guys in class may want to pay attention to this, and I don't know how I glossed over it. This not only happens in aqueous solutions, right? This happens in what we call molten liquid ionic compounds. So what this means is that we're talking about a situation where you heat to a very high temperature the ionic compound until it melts, right? So when it is in a liquid state, the ions are free to move as well. And as a result, in a liquid state, ionic compounds can also conduct electricity. So basically, when it comes to ionic compounds, in the solid state, they will not conduct electricity, but in the liquid state or molten state, or in the aqueous state, they are able to conduct electricity. And the reason for that is because in both states, the ions are mobile. They're free to move around, all right? So that's what basically what we talked about. And then this is just rehashing what I just said about the anode and cathode. And I started talking about non-electrolyte solutions. So basically what I was saying here is that there are three types of solutions that in regards to their ability to conduct electricity. The first one is what we call the non-electrolytic solution. And these are solutions which are not able to conduct electricity because the solutes do not dissociate to form ions. So the example that is shown here is methanol, all right? Here you have your methanol molecules in an aqueous solution. There are no ions formed. And this here is a picture of the setup to show whether or not the solution is able to conduct electricity, which in this case it is not, right? And we know that because the light bulb, which is a part of the circuit, is not lit up, all right? So therefore, as a result, we know that this solution cannot conduct electricity. So we say that it's a solution of a non-electrolyte, all right? Now, I think this is where I'm about to start to talk about when I got you on. So let me go from here. Okay, so the other two types of electrolytes are known as strong electrolytes and weak electrolytes, all right? Strong electrolytes are basically compounds which, when dissolved in water, undergoes complete dissociation and therefore form ions. And therefore, the concentration of the ions will be relatively high, and therefore that solution, as a result, will be able to conduct electricity. So one good example of this would be sodium chloride, right? Sodium chloride is a strong electrolyte. If you start off with solid sodium chloride and add it to water, then if you could see the particles, you'll see sodium and chloride ions floating around, right? And these are charges, okay? So therefore, that solution is able to conduct electric current because of the presence of the charges in the solution. Weak electrolytes, on the other hand, they undergo what we call partial dissociation, and therefore the concentration of ions in these solutions are relatively small, right? A good example of this would be acetic acid. Acetic acid, if you take the acetic acid pure and add it to water, what will happen is that only a small fraction of the acetic acid molecules will go into solution. So therefore, as a result, the concentration of ions will be very small, especially compared to the sodium chloride. So when you compare a 1 molar solution of sodium chloride to a 1 molar solution of acetic acid, whereas here, the light or the lamp or the bulb is lit up very brightly, in here, you see that there's a very faint glow in the bulb here in the case of acetic acid. So that demonstrates that the acetic acid conducts electricity, but not as well as the solution of sodium chloride, all right? So that's the difference between a strong electrolyte and a weak electrolyte. Okay, so continuing our discussion of ionic solutions, I want to introduce to you this symbolism here. The square brackets, this is used to represent the molar concentrations in units of M, which would be moles per liter. So if you see something like this, let me write this down here. Oh, shoot. Why did I do that? Okay, so if you see, I'm going to squeeze it in right here. If you see something like the what's going on? Okay, so if you see something like this, square parentheses, and let's say I put NaCl, and that is equal to 0.50 M, right? So if you see something like this, what this means is that the concentration, or I should say specifically, the molar concentration of sodium chloride is equal to 0.50 M. So basically, the brackets are used to indicate that what's within the parentheses, the concentration of that would be equal to whatever the value is. That's basically what that symbolism means. So you're going to see the symbolism a whole lot, not only in general chemistry 1, but also a whole lot in general chemistry 2, all right? So if you have a solution of 0.010 M sodium chloride, as we said before, sodium chloride is a very strong electrolyte. So what that means is that it will undergo complete dissociation. And we can represent that dissociation, as you can see here, using a chemical equation, where we start with sodium chloride solid to begin with, and then you have an arrow, and then you have the Na plus aqueous and Cl minus aqueous, right? So what does that mean? Based on this equation, we can basically come to the conclusion that whatever the molarity of the sodium chloride that you start off with, the molarity of the sodium ions and the molarity of the chloride ions is going to be the same, right? Because it's a 1:1:1 mole ratio between the sodium chloride solid, the sodium ions, and the chloride ions, right? So one could also say that the total concentration of ions in this solution would be equal to 0.010 m plus 0.010 m, which would be equal to 0.020 m, all right? So that's the total concentration of sodium and chloride ions present in this solution. Okay, we talked about strong and weak electrolytes, and those terminologies, strong and weak, can also apply to acids and bases, right? So weak acids basically are the acids that will undergo partial dissociation. And we met one example for weak acid earlier, acetic acid, right? In fact, the vast majority of organic acids are weak acids. Acetic acid is one such example. And then strong acids are those acids which will undergo complete dissociation to form ions, and then as a result, they are very good conductors of electricity, all right? Now, basically what that means is that in the case of weak acids, as we said before, for weak electrolytes, the amount of molecules, or I should say the amount of ions present compared to strong acids will be very small. So therefore, that's the reason why they're not as good conductors of electricity. So the dissociation can be represented using an equation where we use a double arrow to indicate that the dissociation did not go to completion. And this is how we represent it. In the case of acetic acid, you see those two arrows going back and forth. Basically, what that means is that the reaction is going back and forth. In other words, the acetic acid is undergoing dissociation to form the ions, but at the same time, you have the ions recombining to form acetic acid, right? And you're going to reach a state of equilibrium where the rate of the reaction going forward would be equal to the rate of the reaction going backward, right? And if you have to do general chemistry too, you'll see that that's a very important topic. There are at least, 3 or 4 chapters dedicated to equilibrium systems, such as the one that we see here, all right? So that's the reason why acetic acid is weak. The reaction doesn't go in one direction, it goes back and forth. And as a result, the concentrations of the ions will be relatively small, and therefore the ability of the weak acid to conduct electricity would be very limited. What I'm about to show you is a ball and stick model representation of basically the same reaction, right? So as you can see here, this hydrogen here leaves as a hydrogen ion, and the rest of this would remain with a negative charge on this oxygen right here, all right? Now, this begs the question, how do we recognize or tell the difference between strong acids and weak acids, apart from conducting an experiment to see whether or not they will conduct electricity? Well, there are some general rules, right? Typically, what you'll find is that in most chemistry literature, strong acids are written such that the hydrogen that would leave as a strong acid would be written at the front, such as the examples that you see here, HCl and H2SO4, all right? And then for weak acids, they typically put the hydrogen at the end of the molecule. But let me just say that this is not universally so, because I've seen in some instances where, in the case of weak acids, they actually put the hydrogen at the front, all right? So this is the rule that you're going to use to determine whether or not a particular acid is weak or strong if you're given a question where that is important. And this is basically what we need to memorize, right? For the strong acids. You need to memorize these 6 strong acids, all right? Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric, all right? These are strong acids. Now, there are others. And if there are others that you might encounter in a question, then I'm obligated to let you know. But you should know these 6, all right? Let me just say, well, before I say that, so all these 6 acids will undergo complete dissociation, all right? Now, there's one acid among this list which is a bit unique, and that is sulfuric. That's why you see the little A right here. And the reason why it's a bit unique is that unlike all these other acids, sulfuric acid has 2 hydrogen atoms per molecule, right? Now, that is important for us to recognize because what happens actually in the case of sulfuric acid is that it can lose 2 hydrogens. The first one will be a complete dissociation. You're going to have H plus HSO4 minus. All right? So this is a strong dissociation, right? But on the other hand, the HSO4 minus can itself lose a hydrogen ion, but this dissociation will be weak. All right? So I'm going to label this as weak here. So this is something that you need to remember concerning sulfuric acid. It's a strong acid, but you need to remember that the first dissociation is the strong dissociation, right? The second one is not as strong, and therefore it is weak, all right? So that's something kind of unique about sulfuric acid among all these strong acids right here, all right? Okay, what next? Oh, and let me just say that once you know these, then you can pretty much assume, unless you're told otherwise, that all other acids are weak acids, all right? Okay, the same terminology can be applied to bases, right? Strong bases will undergo complete dissociation in water and also will conduct electricity. So a good example of a strong base would be sodium hydroxide. NaOH will undergo complete dissociation to form Na plus OH minus, right? So that's what happens in the case of strong bases. As you can see, ions are formed, and therefore the resulting solution will be a very good conductor of electricity. Weak bases, on the other hand, are not as strongly dissociating, and therefore the concentration of ions will be low, and therefore weak bases will be weak electrolytes. So an example of a weak base would be ammonia. Now you might be asking, why is ammonia considered to be a base at all? Because if you look at the formula of ammonia, there's no hydroxide. Well, what happens? You have to go back to what the definition of a base is. A base is a substance which, when added to water, produces hydroxide ions. And what happens in the case of ammonia is that when it's added to water, you're going to have this reaction, this back and forth, to form NH4 plus and hydroxide ions, right? So because it produces hydroxide ions, it's considered to be a base. And because this is an equilibrium situation, it's a weak base as a result. All right? So that's basically the difference between a weak and a strong base. A strong base, when it's added to water, undergoes complete dissociation to form a relatively high concentration of OH minus and whatever the other cation is. In the case of ammonia, when it's added to water, it undergoes dissociation to form hydroxide ions and the ammonium ion, but it's a back and forth. It's an equilibrium situation, and therefore, because of that back and forth, the concentrations of the ions are reduced compared to in the case of strong bases like sodium hydroxide. So again, this begs the question, how can you tell the difference between strong bases and weak bases? And basically, this is kind of easier than the table that I gave you to memorize for acids. Pretty much all hydroxides of group 1 and 2 are strong bases. Any other base that you may encounter, you can consider them to be weak bases, all right? So all hydroxides of group 1A and 2A, you need to memorize these as strong bases, and any other bases you can consider to be weak. Okay, I see a question being asked. Okay, so Miss Good is asking, is it weak because there's less hydrogen? No, and unfortunately, I can't go into all the factors that explains why a particular acid or base is weak. All I can say is that if you have to do organic chemistry, you'll learn more about that. It's any answer I give now will take a long time for me to explain, to be perfectly honest. So unfortunately, I can't get into that. I'd love to, but can't get into that right now. But that's a good question. I don't know if you have to do organic chemistry, but if you have to, then you'll certainly learn why it is that acetic acid is a weak acid, for example. I will say this, it has to do with the fact that an ion that is formed, which is the acetate ion, is a relatively strong base, and that's all I can say. It's a long story. All right. Okay. So now that we have covered acids and bases, strong and weak, the next thing we're going to talk about is neutralization reaction. Now, why is this thing not? Hold on. Okay, neutralization reactions, right? So what is neutralization? Stick a pin. Okay. Neutralization reaction. Oh shoot, I printed the wrong. I printed assignment 4, it should be assignment 3, I should have printed. Okay. So let's talk about neutralization reaction. So neutralization is basically the reaction between an acid and a base. And the whole idea behind this reaction is that acids are acidic, bases are basic. When they react with each other, they produce a product which should be neutral. So that's why they call it a neutralization reaction. One of the products would be water, which is definitely neutral, but the other product is called a salt. Now, let me just say that this is not true in all cases. The salt may or may not be neutral, but I won't go into all that right now. Again, this is something you learn in Chem 2, right? There are some instances where the salt is acidic, there are other instances where the salt is basic, and there are yet other instances where the salt is neutral. But the whole idea behind this whole term neutralization is that both the water and the salt will be neutral, because they're suggesting that by reacting the acid with the base, they're canceling out each other, all right? Okay, so we're just going to go with this notion that, you know, all the products, the water and the salt, will be neutral. So that's a neutralization reaction, and we typically use indicators to tell whether or not the reaction is complete. And for those of you, well, one person, who's in my lab, you're going to get the opportunity to actually see this at work when we are doing the experiment where we're determining the amount of acetic acid in commercial vinegar, right? And that will be an acid-base reaction where you're analyzing the amount of acetic acid by doing an acid-base reaction or a neutralization reaction, all right? And we use an indicator in that reaction to tell when you add enough acid or enough base to the acid so as to cause a neutralization to occur. So that's something to look forward to. So what we're going to look at now is how do we determine what is called the net ionic equation, all right? So basically, in order for us to determine the net ionic equation, we have to determine which species remain unchanged on both sides of the chemical equation, right? Those species we call the spectator ions because all they do is sit around and watch what's happening without undergoing any change, right? The actual reaction will take place between the participants in the reaction. And basically, the net ionic equation will show which ions or which particles are directly involved in the reaction. So we're going to use the same equation that we had before for the reaction between a strong acid and a strong base to form salt and water. So I think I glossed over something. Let me go back to the previous slide. I'm sorry. Okay, so one thing I should mention is that the salt that is formed, you can figure out the formula of the salt based on the formulas of the acid and the base, right? So basically, the potassium, which is a positive part of the base, will come together with the negative part of the acid to form the salt, right? And the other two parts, the hydroxide and the hydrogen, will come together to form the water, all right? So that's basically how you can figure out the formula for the salt, because water is always going to be the other byproduct, all right? So basically, if I gave you this, let's say I gave you, let's say I gave you H2SO4 plus sodium hydroxide, right? And I ask you to complete this. Well, you know that water is one of the two products, and the other product would be the product that is formed when the sodium comes together with the sulfate, right? When that happens, the formula becomes Na2SO4, right? So therefore, once you determine that, then the only thing you need to do is to balance this equation, which means that you're going to need a 2 here and a 2 there, and that's it, all right? So that's how you can figure out what the salt is, based on the formulas for the acid and base. So let me go back now to the slide that we were on, and we're going to use this example here, the reaction between hydrochloric acid and potassium hydroxide to form water and potassium chloride. Now, in most textbooks, they call this reaction, for the purposes of determining the net ionic equation, they call this the molecular equation, which is a bit of a misnomer because not all the species involved are molecules. In fact, the only molecule that exists here is the water, right? All the other compounds, well, this can be considered to be a molecule, but it will be dissociated. So it's going to form ions. So, but it's called a molecular equation for the purposes of this exercise we're about to do. Now, that would be the overall equation. The task is to get the net ionic equation. How do we do that? Well, the first thing we have to do is to identify which of these species will undergo complete dissociation, right? And basically there are 3 categories of compounds which will undergo dissociation in water. Strong acid, strong base, or a strong electrolyte, right? So basically what you need to do is to identify which of these species will undergo dissociation. Now, in the case of HCl, it's a strong acid. So when that dissociates, it's going to form H plus aqueous and Cl minus aqueous, right? So that's what happens in the case of HCl. It will undergo complete dissociation to form H plus aqueous and Cl minus aqueous. The same is true for the potassium hydroxide. It's a strong base. So when that dissociates, it forms K plus aqueous plus OH minus aqueous. OH minus aqueous, all right? So that's what happens in the case of potassium hydroxide. Then we get to the right side of the equation. And we notice here we have H2O. As I mentioned before, H2O is a molecule. H2O will not undergo dissociation. So we simply rewrite that down here, H2O liquid. And then we get to potassium chloride. Potassium chloride, you'll notice, has an aqueous symbol here, right? Any ionic compound which has an aqueous symbol in the formula will undergo complete dissociation without exception. So if you have an ionic compound like potassium chloride or sodium bromide, whatever, if you see aqueous, it undergoes complete dissociation. So therefore, we're going to put K plus aqueous plus Cl minus aqueous. Okay, so in most textbooks, they're going to call this the ionic equation for this reaction, ionic equation. All right. Okay, so now we're going to get to the net ionic equation. Let me write that down here. Net ionic equation. How do we determine the net ionic equation? Well, as stated here, we need to identify those species that we consider to be spectator ions. Spectator ions are those species that exist in the same state on both sides of the equation. So if you look at this equation carefully, you'll see that you have a chloride ion here and a chloride ion here. So that cancels out, right? And also the potassium ion here will cancel out with the potassium ion there, right? So therefore, those are the spectator ions. The ions that I crossed out, which are the same on both sides, in every way, they are the spectator ions, and therefore we can cross them out so that we can get the net ionic equation. So basically, to get the net ionic equation, we write down what is left, which would be the H plus the OH minus, which are both aqueous. Aqueous. And the product, the only thing left on the right side will be H2O liquid. And that would be the net ionic equation for this reaction. All right? So basically, just to briefly go over what we just did, we start off with the molecular equation. By the way, make sure that the molecular equation is balanced. I should have mentioned that. Make sure that the molecular equation is balanced, right? Which it is in this particular case, right? So once you get the balanced molecular equation, you identify which species will undergo complete dissociation. And the species that will undergo complete dissociation are strong acids, strong bases, and any ionic compound in an aqueous solution, right? Strong acids, strong bases, any ionic compounds that's in an aqueous solution will undergo complete dissociation. So in this case, the HCl will undergo complete dissociation because it's a strong acid. The potassium hydroxide will undergo complete dissociation, so therefore it's a strong base. The water will not, because the water is in a molecular state. And the potassium chloride, because it has an aqueous symbol beside it, we can assume that that will also undergo complete dissociation. Once we determine that, you identify the ions that are the same on both sides. Those are the spectator ions. All they do is sit around and watch what's happening. Don't participate in the actual reaction. Once you identify those and cross them out, whatever is left will result in the net ionic equation for the reaction. All right? Okay, any questions about this? Any questions? Any questions? All right, so let me move on. Okay, so this is what I was referring to for those of you, or I keep saying those of you, for the one person in my lab, we'll be doing 2 experiments which involves this particular technique known as titration. So basically in titration, it's a method of determining, well, you can use it for different things actually, but one of the functions is to determine the concentration of one solution based on the known concentration of another solution, right? And just to give you a brief description of what is happening in this type of setup, you're going to need a couple of things, a couple of pieces of glassware. One of them is called a burette. A burette is basically a long cylindrical piece of glassware. Let me see if I can find one online so that you know what it looks like. So let me go here and put burette. Chemistry, let me try that. And by the way, this is the English speaking, well, this is the English way of spelling burette. In the United States, it's spelled B-U-R-E-T, so just in case. Okay, so these are some commercially available. I want to find, let me see here. Let me go to images. Okay, let me see this one. Oh Lord, this is small picture. Let's see. Okay, so this is what it looks like. They come in different sizes, right? This one is a 25 mil burette, apparently. The ones that we use in the chemistry lab here is a 50 mil burette. Now, you cannot see it from this picture, but the way this is graduated, it starts with 0 at the top, and then it goes down to the maximum volume, depending on the size. So in this case, if it's a 25, it starts with 0 and ends with 25 here, right? So the key thing you need to remember about the use of the burette is that when you pour a liquid into it up to this mark right here, the amount of liquid that is in it is not the volume of the burette or the volume represented by the graduated units here, right? When you pour liquid into it up to the 0 mark, you're definitely going to have more than 25 mils of the solution in it. And that's because the burette is designed not to measure the amount of liquid that is in it. It's used to measure the amount of liquid that is dispensed from it. All right? So let me explain what I mean. Let's say you add a liquid up to the 0 mil here, right? And you place a beaker underneath here. You have the stopcock here, which you can turn off and on to allow the liquid to pass through. So let's say you have you have the liquid exactly at the 0 mark here. And let's say you want to collect 10 mils of the liquid down here. You basically turn this on, allow the liquid to pass through, and the meniscus here will fall until you get to the 10 mils, and then you turn it off, and then you know you collected 10 mils of liquid underneath it. That's how it works, right? So in the titration process, for the experiment that we're going to do for the vinegar, what you're going to do is you're going to have sodium hydroxide in the burette. You're going to have vinegar, a measured amount, in a flask, which you're going to place under the burette. You're going to add an indicator to it. The indicator that we use is a substance known as phenolphthalein. That substance is colorless in acid and pink in base, right? So the way this is done is that you have your vinegar, you have to add some water to it, and then you add no more than 2-3 drops of the indicator to it. The solution, as a result, will remain colorless, and then you're going to add your base to it. And simply put, what you're going to do is you're going to deliver the base from the burette until you get to a point where the pink color appears, which shows you that the solution, all of the acetic acid has reacted, and the solution is just starting to become basic. So when you see the pink color that remains, you quickly turn off the burette, you record the initial and final volume, and that gives you the amount of base added to the solution in the flask. And then you have to do some calculations and so on, and then you'll determine the percentage. For our experiment, it's a percentage of vinegar, percentage of acetic acid in vinegar. So that's just an overall description of the experiment. In the actual experiment, there's a lot more details because you have to do some other things like standardization and so on, which I won't get into. All right. So that's basically what happens in titration. Let me go back to this right here. Okay. So let's talk about what time is it? Okay, let's talk is that right. Okay. 10:16. All right. So let's talk about certain acid-base reactions which involves the formation of gases. And these are a few examples here. If you have a compound, any compound which contains the bicarbonate ion or the carbonate ion, if you add acid to them, they will perform these reactions as you can see represented by these equations. In both cases, carbon dioxide will be produced, all right? And this is something you can actually do at home. As you can see here in this picture, what this person is doing is taking baking soda. Baking soda is basically sodium bicarbonate, right? And if you add anything acidic to it, like lime juice, because lime juice or lemon juice contains an acid, or citrus fruits, by the way, contains an acid known as citric acid. So if you add citric acid to anything that contains the bicarbonate or carbonate ions, then you're going to see some bubbles forming. The bubbles are due to the carbon dioxide being formed, which is a gas, all right? Another type of gas-forming reactions involving acids is if you add acid to any compound which contains the hydrogen sulfide or the sulfide ion, right? These are the two equations here. Now, this one I would not recommend you do at home because in both cases, they produce a gas which is known as sulfur dioxide, which is a gas which will attack your respiratory system. If you're in a room filled with SO2, you'll be coughing and hacking and all of that. So you don't want to. This reaction will be best done under fume hood. And then we get to any compound which contains a hydrogen sulfide and sulfide ions. If you add acid to them, you're going to get a gas known as hydrogen sulfide. And this reaction you definitely don't want to do at home for two reasons. One, this gas smells very awful. It has the smell of rotten eggs, right? And it's also poisonous, right? So if you find yourself in a room filled with H2S, you smell the rotten eggs at first. The way I heard it described is that you smell the rotten egg smell at first, and then if you stay there longer, you don't smell it anymore, and that's when you're in trouble, right? And then if you stay longer, then you'll die. So you don't want to be exposed to this gas for too long, all right? In any case, so these are just some special reactions involving acids reacting with these compounds containing these ions, and they produce the gases that you see observed right here. Okay, and these are all net ionic equations, as you can see, right? Now, let's talk about another group of reactions that occurs in an aqueous solution. We call these precipitation reactions, right? And basically, a precipitation reaction is basically a reaction which produces a solid when you mix two solutions together, right? So you have two clear solutions, you mix them together, you end up with a solid being deposited. And that solid is called a precipitate. So the example that is shown here, I believe, is the reaction between lead, oh, I hate red. Anyway, lead nitrate, aqueous, plus potassium iodide, solid. No, aqueous, I'm sorry. And you're going to get two products. You're going to get PbI2, which turns out to be a solid, and you're going to get potassium nitrate, which would be in an aqueous solution. So this yellow color solid that you see here is due to the lead iodide, right? So we have two aqueous solutions. When mixed together, one of the products would be a solid, and that solid is called a precipitate, all right? Of course, we have to ensure that the equation is balanced. So we need a 2 here and a 2 here, and the equation is balanced, all right? So that's an example of a precipitation reaction. Now you'll notice, and this is something that you should have met before in your introductory or high school chemistry. You should notice that this is a double displacement reaction. Double displacement, right? And if you don't remember what that is, in a double displacement reaction, you have an exchange of ions between two ionic compounds in an aqueous solution. So we have the lead here combined with the nitrate. We have the potassium combined with the iodide. The lead will combine with the iodide to form lead iodide. The potassium will come together with the nitrate to form the potassium nitrate. That's basically what happens in a double displacement reaction, all right? And most, if not all, in fact, I cannot think of any exceptions, so let me just say all, pretty much all the precipitation reactions are double displacement reactions, all right? So that's what happens in these reactions. Now, the problem that is oftentimes faced when dealing with questions of the type where you're looking at double displacement reaction is predicting which of the products will form a solid, right? And the answer lies in the chart I'm about to show you. And this chart, by the way, is in that packet that I've posted in Canvas, right? So you don't need to memorize this. You'll have access to this during your tests, exams, whatever, right? So basically this summarizes the rules for predicting whether or not an ionic compound will dissolve in water, right? Or will form a precipitate. So basically, if you understand how to use this chart, then you can basically predict which ionic compounds will form a precipitate in an aqueous solution and which will not. So just to highlight a couple of parts of this particular chart, the first line says almost all nitrates, acetates, perchlorates, group 1A metals, and ammonium salts are solvents. So any compound that fits the descriptor or descriptions in that line will dissolve in water. The next line says most chlorides, bromides, and iodides are soluble, but there are certain exceptions. Those of lead 2+, silver plus, and mercury 2,2+. So basically, according to that second line, any compound, any ionic compound which contains a chloride, bromides, and iodides will be water soluble, excepting the ones, the ions that are listed there, and so on and so forth, right? So if you are familiar with this table, then you can pretty much make predictions as to which product will precipitate in a precipitation reaction. And the next slide I'm about to show you gives you some examples of precipitation reactions and their application, right? So for example, in the case of the first one, the reaction between aluminum ions and hydroxide ions to form aluminum hydroxide, that's an example of a precipitation reaction. And this is used for water purification, where if the solution or if the water is too basic, then you can add aluminum ions to it. It forms a precipitate, and you can get rid of the suspended product, all right? And I won't go through the others. You can look at the others on your own, but these are all examples of precipitation reaction. Now, I'm going to show you an example of a question that you could face concerning precipitation reactions and how do you make predictions concerning them. So let me do this and let me open up. I think I'm going to use Word for this purpose. Okay, so let's say you're given okay, I'm going to use the same example that I showed you before. The reaction between lead nitrate plus potassium iodide, right? So you could be given a question like this, and you're asked to write down the net ionic equation, right? So the first thing I would do is I would look up, let's say you're just given this. Sometimes you're given more information, but let's say you're given this, right? And let's say the question is something like, write the molecular equation of the reaction between lead 2 nitrate and potassium iodide. The first thing I would do is consult the table that I showed you before. So let me go back to this right here. And let me make it smaller so you can, what is going on here? Hold on. Okay, okay, so that's the table. Okay, I'm just noticing your question. Oh, she has to go. Okay. Okay, I'll see you Thursday. So let me go back to this now. So okay. So the first thing I would do is I would consult this table to see whether or not these compounds are in an aqueous solution. In other words, are they soluble in water, right? So the first thing I notice is that it says all nitrates are soluble, right? So I will just put AQ here, right, to indicate that it is dissolved in water. And then going back to the table, make this smaller. Okay, so going back to the table, I would look up information about potassium iodide. And what I notice here is that it says all group 1A metal salts are soluble in water, right? And potassium is in group 1A, right? Not only that, but it says that most chlorides and iodides are soluble, with these exceptions. Potassium is not one of those exceptions. So what I would do in this case is put AQ here as well, right? Then I would figure out what the products are. And as I said before, it's a double displacement reaction. Let me make this large, right? So basically, the products of this reaction will be PB, I2, and potassium nitrate, KNO3. And then before I do anything else, I'll balance this equation. So that would be the equation. Now I have to figure out if these two products are soluble in water, right? So what do? I go back to the table, right? Or the chart. And I'll look up information about lead iodide. And look what I see here in the second line. Most chlorides, bromides, and iodides are soluble. Exceptions, those of lead 2+. So that means that lead 2+ will be insoluble in water, and therefore I will put solid here as the state of lead 2 iodide in water. And then now, in the case of potassium nitrate, again going to the table, again, group 1A metal, right? And almost all nitrates. So on those two counts, I can therefore say with confidence that potassium nitrate is in, an aqueous state, right? So basically this would be the molecular equation, right? So now we have to figure out what the ionic equation is, right? And if you remember what we talked about with respect to the neutralization reaction, we have to figure out which species will undergo complete dissociation, right? Now, in this case here, they're all ionic, right? So basically, any compound that is ionic, that is in an aqueous solution, will undergo complete dissociation. So that means that in the case of lead 2 nitrate, it's ionic, it's in an aqueous state. That means that this will dissociate to form Pb 2+ aqueous. And by the way, I should have mentioned this in the previous example, in the case of the neutralization reaction. Whenever you're doing these problems, make sure you include the state symbols, right? Very important. Aqueous, if it's dissolved in water, L for liquid, G for gas, S for solid, right? You have to include those as well. So in the case of lead 2 nitrate, that dissociates to form lead 2+ and 2 nitrate ions, right? And of course, you should understand why we have 2 here, because we had 2 there, right? Then we get to the potassium iodide. And look what we have here. We have a coefficient of 2 in front of the entire compound. So basically, these 2 ions will be multiplied by 2, and it's aqueous, so it will undergo complete dissociation. So 2K plus aqueous plus 2I minus aqueous. All right? So that takes care of everything on the left side of the equation. Now we move to the products on the right side. And the first thing we notice here is that we have lead 2 iodide, but look at what we have here. It's a solid. So that will not dissociate. So we simply rewrite that as the same thing. We don't change anything as far as that is concerned, right? And then we get to the potassium nitrate, which is in an aqueous solution. That will dissociate. So therefore, we're going to end up with 2K plus aqueous plus 2 NO3 minus aqueous. So this would be the ionic equation for this reaction. So the next step is to determine the net ionic equation. So how do we determine that? Well, we have to identify the spectator ions. So what are the spectator ions in this case? Remember, the spectator ions are those ions that are identical on both sides of the equation. So what are the spectator ions in this case? The two potassiums here and here, and the two nitrates here and here, right? So once we identify and cancel out the spectator ions, whatever is left will result in the net ionic equation, which is Pb2 plus aqueous plus 2I minus aqueous to give Pb I2 solid. And that would be the net ionic equation. So these are the steps that you'd have to go through, very similar to what we saw in the case of the neutralization reaction, in order to get from the molecular equation to the net ionic equation. All right. Okay. Any questions about this? Any questions? Any questions? All right. Let's see. Let me go back to the PowerPoint and see what's up next. Oh, okay. All right. I think we're going to finish off by talking about oxidation and reduction. So these are a special group of reactions which you may have met before, but you did not know that they can be classified under these two terms. So firstly, what I'm going to do is define what we mean by these terms, oxidation and reduction. We tend to use the term redox to basically put those two terms together, because in actual fact, in most reactions, if you have oxidation taking place, reduction will have to be taking place as well, and you're going to see the reason why shortly. So basically, in a redox reaction, basically what we have is at the microscopic level, the transfer of electrons from one reactant to another, right? So something will be losing electrons, and then the other species will be gaining electrons, right? The substance that is losing electrons will be said to be oxidized, all right? While the substance that is gaining the electron is said to be reduced, all right? And there's a, what do you call it, a mnemonic that you can use to remember what is oxidation and what is reduction. Oil rig, whoops, sorry. Yeah, what's going on here? Oil rig, right? Oxidation involves loss of electrons, reduction involves gain of electrons. All right, so that should be helpful in terms of remembering the definitions of oxidation and reduction, right? So this is what happens in every redox reaction. Something will lose electrons, and those electrons have to go somewhere, and the substance gaining those electrons will be the one that is undergoing reduction, all right? Now, in order for us to fully understand what happens in a redox reaction, we need to understand this concept of what is known as oxidation number. In some textbooks, they call it oxidation states, right? Same thing. All right. So the oxidation number is specific to an atom in a molecule or an ionic compound. And here's a definition of the oxidation number. It is a charge that the atom would have in a molecule or an ion if the electrons were completely transferred. Now, as we know, in a molecule, you have electrons being shared, right? So this is kind of like a theoretical concept, which is actually useful for understanding what happens in a redox reaction. Now, there are some rules for determining the oxidation numbers of atoms in different situations. And we're going to go through these rules. Now, these rules, you don't need to memorize them, but you certainly need to know how to use them. And what you'll find is that when you use them over and over again, you find yourself remembering what these rules are all about, all right? So the first rule is that any element that is not combined with anything, its oxidation number is assumed to be 0, all right? So any element that is uncombined with anything else, such as these examples right here, right? Even if you have more than one atom in a molecule, the oxidation number of that atom in the molecule is equal to 0 if it's connected to another identical atom, right? So in the case of hydrogen, oxygen, and phosphorus, even though they're all polyatomic, the oxidation number is still 0, right? So any element not combined with anything else, its oxidation number is 0. Okay, so that's the first rule. The second rule is that in the case of monatomic ions, the oxidation number is equal to the charge on that ion, all right? In monatomic ions, the oxidation number is equal to the charge on that ion. Okay, so just to give you some examples, in the case of the lithium plus ion, its oxidation number is +1. In the case of the iron 3 ion, its oxidation number is +3. In the case of the oxide ion, its oxidation number is -2, right? So if it's a monatomic ion, whatever charge is on the ion, that is the same as the oxidation number of that ion. All right. The next rule, it's kind of specific, it's kind of special, has to do with oxygen, right? In the case of oxygen, if oxygen, and this should be worded differently. Let me add, hold on, the oxidation number of oxygen. Let me add here, in its compounds, right? Make a note of that. In its compounds. In other words, if the oxygen is combined with other elements. So the oxidation number of oxygen in its compounds is usually -2, all right? But there's an exception. And the exception is if you have oxygen in hydrogen peroxide or peroxide ions. In those instances, the oxidation number of oxygen is -1, all right? So that's a special rule dealing with oxygen. If oxygen is combined with any other element to form a compound, its oxidation number is usually -2. But the exception is in the case of hydrogen peroxide and in the case of peroxide ions, the oxidation number of oxygen is -1, all right? So that's an important rule that you need to remember. Any questions so far? Any questions? Okay, the next rule, the fourth rule, has to do with hydrogen. This is also a special rule. And again, I have to make a correction or addition here. Where am I going to do it? Oxidation of hydrogen in its compounds. So I'm going to put in its compounds. So again, please make a note of that. So the oxidation number of hydrogen in any compound is +1, excepting if hydrogen is bonded to metals in binary compounds, right? In those instances, the oxidation number is -1, all right? So for example, in the case of hydrogen chloride, the oxidation number of hydrogen in that case is +1, but in the case of potassium hydride, the oxidation number of hydrogen is -1. And the reason why is that hydrogen in this case is bonded to a metal, right? So whenever you have hydrogen bonded to a metal, the oxidation number is -1, but if the hydrogen is bonded to a non-metal, the oxidation number is +1, all right? Okay, the next rule, rule number 5, deals with the elements in group 1A and group 2A and fluorine, right? And it's very simple actually. In their compounds, I keep having to add this. So in their compounds, let me write this here. In their compounds, group 1A metals have an oxidation number +1. Group 2A metals have an oxidation number of +2. And fluorine is always -1, right? So if fluorine is bonded to anything other than fluorine, then the oxidation number of the fluorine in that compound is -1, right? As far as group 1A metals and group 2A metals are concerned, if they're bonded to anything, the oxidation numbers are always +1 and +2 respectively. Okay, now here we get to a rule which helps you to determine the oxidation number of other elements which were not mentioned before. And this rule has to do with situations where you have a molecule or a polyatomic ion. It says the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or the ion, all right? So basically, if you're dealing with a molecule or a polyatomic ion, if you add up all the oxidation numbers of all the atoms in that particular structure, then that total will be equal to the charge of that particular structure. So let me give an example. Let's say you're given the bicarbonate ion, HCO3, and let's say you're asked the question, what is the oxidation numbers of all the atoms in that particular ion? Well, based on the previous rules, we know that the hydrogen here is +1, right? And we know that the oxygen here has an oxidation number of -2. So that is based on rules numbers, I think it was 3 and 4, right? So the only element in the structure which we cannot get the oxidation number of directly is the carbon. But we do know that the sum of all the oxidation numbers, based on rule number 6, is equal to -1, right? So all we have to do is some simple algebra, right? Where we substitute or plug in the values of -2 and +1 into the equation shown here. And you'll notice that we have to multiply the oxidation number of oxygen by 3 because you have 3 oxygen atoms here, plus the oxidation number of hydrogen, plus the unknown, which is carbon. But we know that the sum of all that is equal to -1. And all we have to do is solve for the unknown, right? And when we do that, we end up with the answer being +4 for carbon. And that's it. So basically, even though we do not know or we're not given any information or rules concerning directly the oxidation number of carbon, we can find it indirectly based on the other rules above, all right? Okay, so that's basically how that is done. And this is where I'm going to stop. So, like I said, unfortunately, I printed the wrong handout. So let me show you, I don't remember if I published it, so let me see if I publish it. Where is it? All right, oh no, wait a minute. Oh, okay. Let me just show you quickly where that is located. Come on, come on, come on. Okay, so under files, and then assignment 3. Wait, was it 3? Four. I keep choosing the wrong one. 4. Okay, so let me publish it now. And let me okay, something is wrong here. I need to go back and let me check something here. Okay, I need to look over this because I think I made an error. Because I think most of these questions here, how did I do that? Okay, I'll let you know exactly what the deal is. Oh, wait a minute. Okay, so I am in the right place. Okay. The problem is that the questions are out of order according to the topics that we covered. So based on what we have covered so far in assignment 4, you should be able to do number 8. Hold on. Number 9, number 10, number 11, number 12. Okay, so that's basically it. So questions from 8 to 12, you should be able to do, all right? So I would try them. And if you have any questions, feel free to contact me, if you have any problems while doing these questions, all right? Okay, so it's published, so you can retrieve it there. All right, so that's it. So remember, well, I don't have to tell you guys, the only person I need to remind is Miss Good. So your test next week, will cover chapters 1 to 2. I'm definitely going to post the answer keys. And she was saying that I apparently neglected to send you guys the graded work for number 1. So I'm going to make sure I do that before the end of the day today. So look out for that. All right. I collect it. It's not that urgent because your test is not going to be based on that.
Yeah, you said to be done by Monday, like Tuesday, last Thursday.
Yeah, that's me.
Well, I can just review it.
Yeah, go ahead and make sure it's correct. Yeah. Take care. Yes, ma'am.
I tend to overthink it.
You're one of those, huh?
I am. It's like, I'm like, I printed it kind of weird. For this one, I wasn't sure if I got to the water. get the
Okay, so
grades
this
of
is
water
the
right.
equation, right? So
Yeah,
it says you're starting off with 1 point, okay, 1 point, and then you do the 18 moles to,
find the moles of H2O.
okay, and that gives you that, and then, okay, that's correct. But for future reference,
Okay.
because I think this answer is actually correct. What I would do is, don't just multiply by this and find the answer, and then multiply that answer by this to
Just
find.
do it all together.
Exactly, and the
Yeah.
reason for that is that if you do it stepwise like this, sometimes you'll introduce what is called rounding errors. If you round off too early at the first multiplication and then round off again, then basically it does not reflect the correct precision.
Okay,
So if you do, you see, when you're doing like a string of multiplications, you just calculate it
you
And
can
then-
do it all.
and then you round off at the end.
Okay.
Right. Or if it's a combination of multiplication and division, same thing. You just do all that. Now, where you have to actually round off at each step is if you did something like multiplication at one step and then addition. Because the rules are different. When you're multiplying, you round off to the lowest number of sig figs. And then when you add, you round off to the lowest number of decimal places. So that's where you have to, you stop and say, okay, multiplication, you round off your answer to the correct number of sig figs, and then you take that answer into the addition part, and then you round off to the lowest number of decimal places, right? But in this case, you just do it in one line.
For the moles of oxygen, because it did grams, right? You would have gone to get the moles of H2O to just get the oxygen.
Correct.
So that's the only thing that, like, I guess kind of confuses me. Is it just a single oxygen, or keeping in mind oxygen?
O2,
Two.
right.
Okay, okay, all right.
Because oxygen exists in nature as O2, as you can see in the formula, so keep it as O2, yeah. Yeah, but apart from that, yeah, it seems as if everything you have is correct.
Okay. You know,
No problem. Okay, so I have another group of students here to antagonize me.
see you later.
Yes, ma'am. Morning. Oh, let me get out of this Zoom here.